All right, so for this lesson, we're going to be talking about measures of central tendency. And you actually use these things all the time, and especially the mean. And then the other ones you've absolutely saw before. Probably you haven't formally used them since like grade 7 or 8, but I'm sure that they will ring a bell. So first is the mean. And the mean is also known as the average. And it's just a way to represent a whole set of data with one number. And basically what we do is we add up all of our data points and we divide by how many data points we added up. We all use averages all the time. Anytime we get a report card, the first thing we do is we calculate our average. I'm sure you've done it with your Teach Assist marks. So we use the mean all the time. Universally, we are always calculating averages. It is really powerful, but as we go through, we'll talk about some of the issues with it and then some other tools we can use just to get a better sense of what's going on with our data. The next one is the median. Similarly, what it's trying to do is give us one number that's a representation of a whole data set, and the median is our middle number. Now, it's important with our median that we arrange all of our numbers, smallest to largest, to then find the middle number that way. If all of our numbers are not arranged, we can't find the median. So just ensure if you're ever finding the median that you do make sure all of our numbers are in the proper order before you get started. Now, we actually use the median a lot in schools. So when you get your report card, you'll notice that it doesn't have the class average on it. It actually has the class median. Typically, because we only have 30 students, or even right now only 15, the median and the mean are usually pretty close in a smaller data set. But it is something to keep in mind that on your report card, you're actually seeing the median, not the mean, which is kind of interesting. Finally is the mode. And the mode is the most frequent data point. Now, the mode is an interesting one. The mode works really, really well for qualitative data. For example, if I'm asking everybody in the class what their favorite ice cream flavor is, the answer that's received the most is a good representation of what ice cream I should buy the class, right? But sometimes with a number, it's not always the best representation with the mode unless it's the mode by quite a lot. Now, the other piece with the mode is you can have two modes. I can also have no modes. So if all of the numbers occur the same amount of times, I could certainly have no mode. That's possible. I could also have multiple modes. That's also possible. So when you're using mean, median, and mode, it is important just to understand some of the issues with them and that they're not always a perfect representation and that maybe there are some more calculations you could do to get a better sense of what's going on with your data. Now, the next piece we'll talk about are equations. So the only one here that has a formal equation is our mean. And we've calculated the mean in our lives tons and tons of times. But this is the grade 12 version of the equation. And if you've ever looked up the equation for the mean, this is what you would have saw. Now you'll notice here we have two different equations. We have the mean of a population and the mean of a sample. The only difference here are the variables and how we denote the mean. The first one is the mean of a population. Now what a population is it's the entire group. We're not missing anybody, or it's all of the possible data points. We often use the mean of a population when we're talking about continuous random variables because we're trying to get all of those points in between, for example, 1 and 2. We want all those points in between as well. So for our purposes right now, we will be primarily looking at samples. But whenever you are looking at the mean of a population, or that's the value you are given, it'll always be denoted by this little mu here. We still find it by adding up all of our data points. That's what that sum means there. And then dividing it by the total number of data points, which is our capital N in this case. Now, for our purposes right now, and until we get to those continuous probability distributions, we will be looking at samples. And basically, this is when a smaller group is taken from the population and analyzed. And so, in this case, we denote the mean by X bar instead. So X with a flat little hat on top. And again, we still just add up all of our data points and divide by how many data points we added up. Exact same equation, slightly different notation. But it is important that we know which one is which, and that is because of this next equation that we'll look at. So this is the part that's new. And now we're going to look at measures of spread. Basically, what we want to look at is how spread out our data is. So to give you a bit of an example, let's say our class average was 80%. There's a few different ways that this could happen. We could have everybody in the class has an 80%, and therefore our average is an 80%, right? If every single person had a mark of 80, then our average would be 80. We can also have where marks are a little more all over the place. And then when we take our average, we end up with 80. Now, those are two very, very different situations, but they both have the same average. Now, looking at measures of spread gives us a way to distinguish between those two options. So a couple definitions. First is deviation. And what deviation is it's how far our data points are from the mean. So what is the distance from my data point to the mean? Is it really far? Is it really close? That's really what I want to know. Now, this leads us to the first thing that we will be calculating, and we'll be looking at what's called standard deviation. And what this does is it quantifies the amount of variation in a data set. In other words, what it does is it gives us a number that we can use to understand if one data set is more dispersed than another. Now, the formulas are a little bit complex. We're going to break them down a bit when we use them together. So first is the standard deviation of a whole population. Again, we'll be using these more when we're looking at continuous probability distributions, or you would use it if you had literally every possible data point. And when you are looking at a population, we denote our standard deviation with a little sigma here. Now, when you draw this out, it looks like this. Kind of looks like a theta. That's not a theta. That is a little sigma there. And what I do is I take all of my data points and I subtract the mean in here, and then I square all of those values. Once I've done that, I add them all up, all those values I got, divide it by the number of data points I have, and then square root it. Now, again, that's a pretty complex formula, so I'll show you how to break it down a bit. So that's for a whole population, but we also have an equation for a sample. And the sample one is very similar. However, we do have it denoted by S, so the notation is slightly different. In addition here, you'll notice we have X bar in here. That's because that is the mean of our sample rather than the mean of a population. And finally, instead of dividing by n, my number of data points, I'm dividing by n minus 1. So my number of data points minus 1. Now, the reason why we do this is that typically with a sample, our standard deviation is a little underestimated. This is because we're just looking at some of the points. So it's very likely that there are some more spread out points that we're missing. So it does underestimate our standard deviation a little bit. So we subtract 1. So we're dividing by a smaller number, therefore increasing our standard deviation just a little bit. We also have variance. Now, for our purposes, we're not going to use variance too much, but it is really valuable for us to talk about. Now, variance is the mean of the squares of deviations in a set of data. In other words, it's the same thing as our standard deviation, just squared. So instead of us square rooting it, we just take it, we square it, and get rid of that square root sign. That's really what we're doing. And you'll notice that the notation is the same as our standard deviation, just squared. Now, the reason why variance is important is because variance is used in a lot of other equations if you continue forward with statistics, and it's very, very powerful. For us right now, we're going to focus on using the standard deviation, but the variance is really beneficial in the future. So it's very worthwhile for us to see, but we're honestly not going to use it too much. So that is all of the intro to this stuff. Now let's do an example. It's a pretty big example, but we'll just do one all together. Are there any questions before we start our example? Not yet? Okay. If there are, feel free to type them as usual. But we can probably get started. Now, I apologize that this example can get a little tedious, but it is really important for us to calculate this by hand and understand what's going on before we start doing these kinds of calculations with Google Sheets or Excel. So here's our situation. The average monthly temperatures for 3 cities are listed below, and keep in mind the data has already been reordered for us, so we don't need to do that. So we're given some data about 3 cities, Mathland, Trigtown, and Algeville. And these are average monthly temperatures. Now the first thing we want to do is we want to determine the mean, median, and mode temperatures. So we're going to be using a sample here. Now it's given to you that it is a sample, but based off the situation, we can also determine that it's a sample. The reason I know it's a sample is we just have one data point per month. That doesn't mean that every single day in that month had the same value. We're really looking at a subset of all of the values and just picking a sample of all of the possible temperatures in this year. So that is why it's a sample. That's important later on when we go to calculate the standard deviation, because remember, the formulas are slightly different. So what we're going to do is I'm going to do one with you, and then I'll give you a moment, a couple minutes to try the other 2 on your own, and then we'll go through the answers. So the first one that we'll do together is Mathland. And the first thing that we're going to do is we are going to find the mean. So we'll start by finding the mean. So because we're looking at a sample, we use x bar, and that is equal to the sum of all of our x's divided by our number of data points. So what I'm going to do is I'm going to add up all of my values for Mathland. So 4 plus 4 plus 6 plus 10 plus 11 plus 14 plus 16 plus 19 plus 22 plus 23 plus 25 plus 26. When I do that, I will get 180. And I divide that by how many data points I have, which is 12, which makes sense because they're the average temperature each month for an entire year. So it makes sense that we have 12. Then I just divide those and I have an average monthly temperature of 15, or sorry, an average yearly temperature of 15. Now I also need to find the median. So if you need a bit of a visual to find your median, once everything is lined up in order, what I like to do for the median is I like to cross off the ends, then the next one, then the third one, fourth one, fifth one, until I get to the middle. It just helps to give me a little bit more of a visual. And now in the middle, I have 14 and 16. Now, because I have an even number of data points, I don't just end up with one number in the middle, which means I need to figure out what number is right in between 14 and 16. Now here it's pretty clear that it's 15, but let's say it wasn't clear. We had a much bigger gap in between the numbers. What I could do is I could take my 2 numbers that are in the middle and divide it by 2. So that will give us 15. Finally, our mode. So the mode is the number that occurs the most. So if I look through the Mathland data, I have 2 4s, and that's the only one that is a double. So my mode is 4. So now I want you to quickly do the other ones. I'll give you 3 minutes to do that, and then I will show you the answers. So I'll give you a quick 3 minutes, and then we'll continue on with the next piece. But it's important that everybody tries that and has it written down on their page. Sorry, I think my mic was off. So here are the solutions. Hopefully everybody had enough time to go through and do those. I just don't want to keep everybody too long. But these are the mean, median, and mode for these 3 different cities. Now what we want to do is we want to look at this data and we want to think about what it's telling us. So let's say that instead of being given all of the data, we were just given the means of all of these places and the medians of all of these places. The modes are so different that they kind of tell us something's up, but if we were just given the means and the medians, we want to think about what would I say about this data? Or what would I say about these 3 locations and their temperatures? Now, if I looked and all of their means were the same, and all of their medians were the same, I would probably say that the temperatures in these cities are very similar. Now, we know that that's not true. We know that some are more all over the place than others, especially from us just looking at the data. So what we want to do is we want to try to figure out how different they are and try to figure out which one is the most different. And that leads us to our standard deviation. So for our standard deviation, this is our formula. Again, we're using a sample here. So we're going to find all of our values, subtract the mean, square it, add them all up, divide by n minus 1, and then square root it. So I'm going to show you how to break down all of these steps just to keep ourselves organized and ensure that we're doing all of the steps without getting too jumbled because there's a lot going on here. So we're going to do, just like before, we're going to do Mathland together. And then you can try the other ones on your own and I'll show you the answers. Then we'll make some quick conclusions at the end. So what I'm going to do to start is I'm just going to write out all of my data points again, just so that I have them in the chart, and then I'll continue to do the next steps. So here are the data points for Mathland. So I have 4, 4, 6, 10, 11, 14, 16, 19, 22, 23, 25, and 26. So that's just all of my data points just to help myself keep track of what's going on. Now, the next thing I want to do is I'm going to do this inside part of the brackets first. So what I'm going to do is I'm going to take each of my data points and I'm going to subtract the mean. Now, just as a reminder from above, our mean is 15. So I'm just going to subtract 15 from all of those data points. So we'll have negative 11, 11, negative 9, 5, 4, 1, 1, 4, 7, 8, 9, and oops, 7, 8, 10, and 11. So all I did is I subtracted 15 from each of my data points. Essentially what I'm doing is I'm trying to figure out how far away from the mean each of these data points are. Now, what we're going to do is we did that middle bit. Now I'm going to square each of those. So 11 squared is 121. 9 squared is 81. 5 squared is 25. 4 squared is 16. Negative 1 squared is 1. 1. 16. 49. 64. 100. 121. There we go. So far, I've done the middle bit, subtracting the mean, and I've done the square piece. Next, what I'm going to do is the sum piece, and I'm going to sum that third column. I'm going to find the sum of the third column and add up all of those numbers. So 121 plus 121 plus 81 plus 25 plus 16 plus 1 plus 1 plus 16 plus 49 plus 64 plus 100 plus 121. And that gives me a sum of 716. So 716 represents this whole numerator there. That is what I've done so far. So what I'm going to do now that I found the numerator is to find my sum, or sorry, my standard deviation. I'm going to write out my formula again. And we did find our whole, oops, that's not 71. It's 716. Sorry, I didn't write the 6. And then we will have the square root of 716 all over 12 minus 1. This 12 here is my number of data points, same n as it was in my mean. And when I put this into my calculator, I'll get 8.07. So now what I want you to do is to try the other two. We are a little tight on time, so we'll see how far we get. I'm going to give everybody 5 minutes to do that, and then we'll make a few conclusions, and then we'll be done. So I'll give everybody 5 minutes, and then we will just take up the last bit, and we're good to go. So 5 minutes to try the other ones and see how those go. All right, so hopefully we've had a moment to do that. I know that it's really long and everybody might not be done, but I don't want to keep everybody here too long. So I figured we can go through the solutions and you can absolutely reference them as well if you want to look at them later. But I know that the process of this can take a long time. So with that being said, if I were to give you something like this on an assessment, I would really ensure that it wasn't too long, just because you can clearly see how long this will take, especially the third one when you don't know those squares off the top of your head. But here are the solutions. So if you're not quite done, don't stress. I just don't want us to run out of time. So the standard deviation for Mathland is 8.07. For Trigtown is 3.05. For Algaeville is 20.13. Now, what this means is that Algaeville's data is far more spread out than Mathland and than Trigtown. If my data was perfect, so if all of my data points were equivalent to my mean, so for example, in this case, if my mean was 15 and the average temperature each month was also 15, my standard deviation would be 0 because all of my points are right on the mean. So there's no distance from the mean, they're all right there. So the larger your standard deviation is, the further from the mean your data points are. That's what that means. So here, because Algaeville's is so much higher, we can see that they're more spread out. So the conclusion that we can make from this is that the temperatures of Mathland and Algaeville are much more spread out than Trigtown. Again, what this means is that that number 15 is probably a better representation of the climate in Trigtown than it is of the other numbers. That is still its average. That's the truth. There's nothing wrong with that number. We just need to also be mindful of the fact that the data there is so much more spread out than it is for Trigtown. So that is our whole lesson there. I'm just going to end the recording.